All right, let's get started. All right, we're going to review the practice exam that Joe gave. And we'll just go through all the 24 questions that he had on it. Does anyone have any questions at the beginning? Any questions about the test or what's going to be on it, or yes?
Yeah, maybe it's too specific. In the past, for this test, do people typically finish in enough time, or is it a big time constraint?
Are you going to be able to finish in time, you say?
Yeah.
He said that this one won't be as long as the practice test that we're going to go over today. But because of that, it may have harder questions. So it's a trade-off.
Yeah.
So I would suggest going through all the questions that you know that are easy. Get through those as fast as you can. And or get through the ones that have the most points. Generally, all the questions should have the same amount of points. If that's the case, do all the questions that you know how to do for certain, 100%. And then go back and work on the others. So just get as many points as you can that you know. Any other questions? Yes?
So I can see Aaron's filming this. Is this going to be available? This review session is going to be available?
It's available right now. It's live.
But then after it's done?
Yes, it will be available at least until the midterm. I don't know how long Joe's going to keep it up.
Cool.
He suggested, since I'm giving out answers, that it may be deleted. But
Like
it'll
after
be
the midterm?
like after the midterm, if at all. Or maybe after the semester, I don't know. It's up to him. Any other questions? About where it is, what time, the test, everything? Okay, let's go ahead and get started. We have 2 hours. We have to squeeze through this test. It's very long, 24 questions. And we barely got through it the previous review. So, Aaron's also a...
Something wrong up here. It's right on that projector. I don't know why this one's not.
I have no idea.
Probably should have caught that sooner.
Was it on panel?
Has it been like that the whole time?
I think so, yeah. Enter the IP address at the top of the screen into your browser. I don't know how that helps, but...
Put it on the intro screen for a second. All right, technical difficulties fixed. So let's start with the master theorem. What should be on your cheat sheet? You are allowed to bring a cheat sheet. It can be 1 page, average size, you know, the 8x11. Both sides, written or typed. I've seen people type very, very small, print out very small print. So that's okay as long as you can read it. 1 sheet, both sides. I would have the master theorem on the sheet. Joe may or may not have it on the test, but you should have it on your cheat sheet just in case. Just an easy way to remember the master theorem is you're going to compare log base b of a with d. Whichever one is the largest, you put that as the exponent on n. So if log base b is larger, then it's O of n to the log base b of a. If d is larger, then it's O of n to the d. If it's a tie, then it's O of n to the d log n. So just think you're comparing the two, log base b of a and d. Whichever one's the largest, you put that as the exponent on n. If it's a tie, do a combination of the two. Yes?
Do we have calculators available?
Probably, but we'll ask Joe right before the test. Sometimes he says no, but
So
usually he says yes.
maybe.
Most of the problems in the test, you won't need a calculator. Because it's not whether you can add large numbers together, it's do you understand the concept. So he'll have very small numbers on things. So you should be able to do it in your head. Like comparing log base 3 of 9 is 2. So, and then you're going to compare that with maybe 1, and you got to decide whether 2 or 1 is bigger. So you should know your logarithms and so forth, and your exponents, and how to multiply them together and add them together and so forth. So let's start with the first question. The worst case of 4 algorithms are carefully timed on dense graphs with n vertices. The Bellman-Ford binary heap of size n, which is the delete min, sparse directed graphs with n vertices, strongly connected components, and n-bit integers, Karatsuba multiplication. The difference, a difference of computer is used to time. A different computer is used to time each implementation. The result of the timing experiments are summarized below. All times are expressed in the same unspecified units. So when I look at these, I'm seeing how they're going to change. Then I'm going to look down here at these different algorithms, and I'm going to think of what is the complexity of those. And then I'm going to try to match them up. If I look at algorithm W, how is it changing when the doubling of it? Multiplying by 8, so that implies what? N cubed. The next one, it just goes up a little at a time.
That'd be log.
Log. The next one goes up. Every time you double the input, it triples the output. Not n squared. N squared, it would quadruple. Now, if you look at... Huh? It's a little bit less than n squared. Huh?
Like into the 1.
Into the
1.59.
1.59, which is what? Karatsuba. There you go. And then the last one is linear. As the input doubles, the output doubles. So that's linear. Suggestion. I give a suggestion that you put every single algorithm that I mentioned today that we've learned in class on your cheat sheet. Put the best case, the average case, and the worst case for each of the algorithms. He mentioned 4 sorting algorithms. Put those on. Merge sort, quick sort. What are the others, Aaron?
Insertion sort, selection sort.
Selection sort and insertion sort. Put the best case, worst case, and average case for all of those sorts. Bellman-Ford, worst, best, average. Delete min, worst, best, average. SCC algorithm, Karatsuba. Have all these on your cheat sheet because they will be on the test as they are here. So, now that we've looked at these, Bellman-Ford is what? What's the complexity of Bellman-Ford? N cubed, which is algorithm. Delete min is what? Log, and which algorithm? X. Then the SCC algorithm is linear. And we're talking about up here, the worst case. And your questions, if you have to read them 2 or 3 times to yourself, go ahead. Make sure you're dealing with the best case, the worst case, or average case. And every question is going to be different. Make sure you're dealing with directed or undirected. You know, just read your questions 2 or 3 times to yourself to make sure you understand it. If you read one word wrong, you can miss everything on the question. Then the next one is Karatsuba, which is algorithm what? I suggest going back over that Karatsuba. There's another question on Karatsuba that we're going to talk about later on the board that we had fun with the previous session. That nobody understood. So, in each of the modular equations below, solve for x. In each case, x must be, it's just that subject you can't cover in 10 minutes.
No.
It's like a whole class. In each case, x must be a non-negative or negative integer less than the modulus. So we need to solve for x in each of these. X plus 3 congruent with 1 mod 7?
5.
So why is it 5?
Because 5 plus 3 is 8.
5 plus 3 is 8. 8 mod 7 is 1. And we want 1 is congruent with 1. So 8 and 1 are congruent. Yes,
So
sir?
when you say congruent, does that mean equivalent to?
No. Equivalent would be, well, equivalent is kind of ambiguous. Equals means they're the same number. Congruent means if you mod them by that modular number, mod 7, if two things are congruent, mod 7, that means the answer is the same.
Okay.
So all numbers are congruent if they differ by the mod. So if we say 8 mod 7, that equals 1. If you add the modulus number 7 to 8, you get 15. 15 mod 7 is 1. Add 8 again, 23. 23 mod 7. It's 22 mod 7 is 1. So we started off at 8, 7. 8 plus 7 is 15. Then if you add 7 again, you get 22. 22 mod 7 is 1. Add 7 again, you get 29 mod 7. You can add 7, the modulus number, as many times as you want, or subtract 7. If you say 8 mod 7 is 1, subtract 7, you get 1 mod 7 is 1. Subtract 7 again is what? Negative 6. Negative 6 mod 7 is 1. All of those numbers are accurate, but the number you want to put on the test is the congruent number that falls between 0 and the modulus number. So negative 6, 1, 8, 15, 22 are all congruent mod 7. But the answer is the one that's between 0 and 7. So the answer would be 1. But here you're answering, you're just figuring out what x is. So let's go to the next one. What is x there? Excuse me?
Sorry, what was the answer?
The answer to the first one is 5. The next one, 5 times 4 is 20, so we need something congruent with 20. So how do we find something congruent with 20? You can either add 6 multiple times or subtract 6 multiple times, or 7. It's mod 7. So if we have 20, subtract 7 is 13, subtract 7 again is 6. And we want to subtract 7 until we get a number that's between 0 and 7. So the answer is 6. If you put 20 or you put 13, you may get partial credit. May. Depends on how good a mood Joe's in. Okay, then the next one is we want to start using our tricks now for exponents. When you find two numbers that are congruent, if you take them to the same power, if you take two numbers to the same power, that number, one number taken to a power, and a congruent number taken to a power, they're still congruent. So if the bases are congruent, if you take them to the same power, they're also congruent. So what we want to do here is find a number that is congruent with this number that's highlighted on the screen. And so how do we find a congruent number again? We add or subtract the mod. So if we subtract the mod here, what do we get? We don't want to add because then it would get too big. We subtract the mod, what do we get?
1.
We subtract the mod, what do we get? Negative 1. Negative 1 to the many times you want, what's the answer? If it's even, what's the answer? If it's odd, what's the answer? Negative 1. So we have an even number, so it's 1.
Oh.
So then what is x?
1.
X is 1 then. Because now we have 1 is congruent with x mod something, Well, 1 is congruent with 1. Now this next one is a little trickier. You got to use some more tricks. And sometimes you want to factor out something from the exponent. Anybody have an idea? Yes?
You factor out all the, you do like a 7 squared, and then you do times 7, and then you mod each of those separately.
Right, right. Because we, see, if we tried to pull out, if you remember 7 to the A to the B, 7 to the power of A, and then take that whole thing to the power of B is the same as 7 to the A times B. So we can factor it out and put it as a double power, if that makes sense. So we can factor out 7 squared, but this is an odd number. So first, let's just factor out 1 7. We could just factor out, should I write on the board?
Yes, please.
Yeah.
So we have 7 to some long number, and it is odd. So what we want to do is factor out 1 7 and make it an even number. Now that it's even, we can factor out a 2 in here, and then whatever that number is divided by 2. So 2 times this number was the original number. Well, with the exception of the 7. So now we have 49, we have 7 times 49 to a high number, mod 48. How do we find a congruent number to this? Subtract or add 48, right? So if we subtract 48, we have 1 to a high number, mod 48. Now this is just 1, so now we have 7 mod 48, and the answer would be 7. 7 mod 48 is 7. So x is 7 in that case. Any questions on that? Okay, let's move on to the next one. This one I want to skip because Joe covered it in class extensively. So can we skip this one? Thank you. So we don't have time anyway. If you have any questions, then maybe you can come see one of the TAs tomorrow. Okay, so number 4. For each pair of functions below, write theta of g if f is theta of g. So if it's theta, go ahead and put that initially. If it's not theta, then put O of g if it's O of g and omega if it's omega. So do it in that order. Because it could be theta and O and omega all at the same time, right? So you want to, if it's theta, put that first. So when we look at this, what is the answer to the first one? If you got n cubed and n squared. First one would be omega, right? When we look at the next one gets a little tricky. Does anyone have a clue on that one, how to do that one? So if you recall, Joe was doing a calculation on n factorial. And he said like 1 times 2 times 3 times 4, clear up the n, would be less than just n times n times n times n times n times n, right? And he was saying that if we calculated the n times n, whatever it was, the factorial would be less than it, right? So in our case, that's about the closest thing we can come. So let's go ahead and use that example, and we would get n to the n. And if we had n to the n, log of n to the n, what can you do on an exponent when you're doing a log?
You can bring it to the front.
You can bring it to the front. So now you have n log n, right? And you're comparing n log n with n log n, so the answer would be theta.
So sorry, but didn't we just say that n factorial couldn't be more, or it's going to always be less?
It's always going to be less.
Right, so then wouldn't that change it can't be theta then, right? Because that means that's tightly bounded on both sides.
It's close enough.
Okay.
More details we'd have to talk with Joe, but this is the calculation that we're going to use. This is close. It's just like when you say something is, just like when something is big O of n squared, is it exactly n squared? No. If it's n cubed, is it exactly n cubed? No. It could be n cubed plus n squared plus n plus log, you know. You just get rid of the rest. Everything, you just use the largest. Yes?
Oh, sorry, could you maybe do that log n factorial on the board?
Sure.
I generally follow that.
Forgot my other computer with the touch screen, so I can't write on my screen like Joe does, so maybe next time I'll do that. So we have n factorial is 1 times 2 times 3 times 4, clear up to n, right? We could also say that go n times n times n times n, and this is going to be greater than that. When he was doing a calculation, he was saying that this was greater than n factorial, so we could use this as an upper bound on what we were trying to calculate. But this is going to equal n to the n, because you have n and it's n times. And when you do log of n to the n, it's going to be the same as n log n, because you can take that exponent and put it in front.
So it seems like a lot of these are just kind of knowing your algebra.
Knowing your algebra, yes. Knowing your algebra, knowing your exponent tricks, knowing your logarithmic tricks. Reminds you back when you were taking math. Then the fourth one is 3 to the n times 8 to the n over 2. Anyone have an idea on how to do that one? So once again, we can try, on this one we can use the factor. Over here we have, what was it, 3 to the n, and we're comparing it with 8 to the n over 2. Now if you recall, a to the b to the c is equal to a to the bc, right? Is that correct? So if that is correct, then this is the same as 8 to the n, 8 to the 1/2 times n, right? Which is the same as 8 to the 1/2 n. Is that correct if I use that rule? 8 to the 1/2, what's the square root of 8? It's about 2.82 to the n. Which is bigger? 3. So the answer would be omega. Number 5, use the master theorem to derive a tight upper bound on the following two recurrences. So first one we have a equals, b equals log base 7 of 8 is, log base 7 of 8 is, it's a little bit more than 1, and d equals 1. So that means log base 7 of 8 is greater. So the answer would be O of n to the log base 7 of 8. Correct?
Yep.
Because you take the larger one. And if this was, if A was 7 and B was 7, then it would equal 1, D would equal 1, it would be a tie. But in this case, it's a little bit more. A lot of times you don't have to know exactly what the fraction is, just that it's a little bit more than something else, or a little bit less. The next one is log base B, which is 2 of 4. What's the log base b of 4? B of a. Log base 2 of 4 is 2. Base 2, so 2 to the 2 equals 4. So the answer is 2. What is d? 2. It's a tie. So on a tie, you do O of n to the d, which is O of n squared, and then log n. O of n squared log n. You guys do have the answers, right? Joe released the answers.
Yes.
So if I say any answers wrong, let me know, yell out. Because I'm just calculating them as I do them. Suppose you have a minimum binary heap containing the integers 1 through 15. The levels of the heap are numbered 1 through n, where the root is the first level, and there are n levels in all. Answer the following questions about this binary heap. What number is stored at the root? 1. Everyone should have that. It's a minimum binary heap. The smallest number is always at the root at the top. Does everyone know what a binary heap is? A minimum binary heap. You guys all remember? Okay. So what is n in this case?
Log of 15 rounded up. So 4.
So 4. 1 at the top, next level is 2, 3, then third level is 4, 5, 6, 7, then 8, 9, 10, 11, 12, 13, 14, 15 at the bottom. So 4 levels. That's if everything was in order. Now if it wasn't in order, he's saying what's the smallest number that could be on the bottom level?
4.
You say 4? Anyone say anything other than 4? So how can you get 4 on the bottom when everything below the numbers need to be larger? You're going to have 4 on the bottom, 5 is going to be at a higher level. How is that going to work?
It's taking the right branch.
It's on the right branch. Does that make sense? And then, what is the largest number that could possibly be in level 2?
9.
9, 9, anything else? So explain why it can't be higher than 9.
If you draw the picture and then look at that graph, there's 6 nodes below. So you just do 15 minus 6.
Right. So if 9 is on the second level, there is going to be 6 nodes below it, 2 below it on the next level, 4 below it on that next level. So that's 6. So you're going to have 6 numbers that are greater than 9 for the binary tree to be correct. Do I need to draw that, or does everyone understand?
Draw it out.
Want me to draw it up? Okay. So if we had a binary heap, 1 is at the top, 2. Let's imagine that we have 4 levels. We got 4 levels. This is how 4 could be on the bottom level. Then on the second level, I put 5 here. Then I go 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is how I can get 4 down here. And we still have everything that is below a number is greater. And this is how I can squeeze. Well, okay. I wanted to draw it with 9 there. So to redraw it with 9 up there, I could go 3, 4, 5, 6, 7, 8, then draw 9 here, 10, 11, 12, 13, 14, and 15. So now I have 9 on the second level and 4 on the fourth level in the same tree. Indicate whether each of the following is the best practice for making timing measurements by writing yes or no. Don't measure small intervals. Yell it out.
Yes.
Account for timing overhead.
Yes.
Avoid cold starts.
Yes.
Time nothing that uses the heap.
No.
What would that mean? I've seen some really crazy things Joe puts in here. I don't know how people miss it. Each of the following algorithms has a theta of n worst case. What was it again? Theta of n worst or best case? Worst case. Get that stuck in your head when you read it. So it is a theta of n worst case. What does that mean? The worst case is not going to be worse than linear or better than linear. Just the worst case is always linear. Give the average case complexity of each. So looking up an n-element hash table, looking in an n-element hash table, what is the average case? Anyone say anything other than constant?
Sorry, I actually have a question. So how do we know to use theta as opposed to O or omega, just to be more explicit here? Sorry, it's not in the instructions or anything.
It is not. So just since he used theta up there, I would just use theta in the answer.
Okay.
He didn't specify, and since he's talking about give the average case complexity,
That's why.
I would just give theta in this case.
Okay.
But I can't guarantee you it'd be wrong if you used. Well, think about, is it really theta or is it big O or is it omega? You got to really kind of think about it. And in this case, it would be constant, and that's not an upper or lower bound. It's both.
It has to be both.
Okay. So looking up an n-element binary search tree.
Log in.
Looking in an n-element binary search tree, which is, yell it out.
Log in.
Okay. Partitioning an n-element array around a pivot. Yell it out.
It's n, but I don't know why.
So when you're doing a partition, I won't go over what we talked about in the last group. You're looking at the ends and you just go in and you compare them. And if you have a big one at the wrong end or a small one, you swap them. And you just do it till you finally get to the middle. You only look at everything one time. So it is linear. Is that right, Aaron? Aaron's also a TA, so I'll be referring to him. He's going to watch my back and make sure I don't say anything wrong.
Are you saying that the pivot is hitting every element at one time? Is that why it's...
No, the algorithm is looking at everything just one time, and they just move in. When you start the partitioning, you just move in. You may move here a couple times. You may move here, but when you're done, you're going to end up at a pivot, and everything on one side is larger, everything on the other side is smaller. But you only look at everything one time, so it's linear. They're not in order, but they're just everything greater is on one side, everything smaller is on the other side.
And that's why like quicksort is n log n, because it takes log n to find a pivot and you do it n times. Is that?
Yeah.
Okay.
Adding to the end of an n-element dynamic array. Constant. Okay, use big O and omega notation. This one was very clear on putting it. To give the tightest possible upper and lower bound on the time required to determine whether there is a path between every pair of vertices in an undirected graph with v vertices and e edges. So we need to find out if each vertice has an edge to all the other vertices, correct? Say, raise your hand if that's correct. Did I repeat that correctly? Did anyone catch a flaw in what I said? Yes?
Did you say edge and not path?
I said edge and not path. The question says path. So be careful when you're taking the test and read every word correctly. A path is different from an edge. A path is a series of edges. It may just be one edge. An edge is just one edge from vertice to vertice. Don't confuse the two, they're different. Because the answers will be different. So make sure you read it properly. So it is a path. There is a path between every pair of vertices. Yes?
A pair of vertices.
A pair of vertices. U and V.
Okay.
You just pick two vertices randomly. Is there a path between them?
So like the whole graph is strongly, what is that? one phrase?
Well, this is undirected, correct?
Oh, yeah.
This is undirected. So, is there a path between every vertice? From every pair of vertices? There's a path. Is there one now? Does that answer your question?
Yeah, that's a good thing.
So, do this once, assuming that the graph is represented with an adjacency matrix and with a list. So, upper bound on the worst case on a matrix. V squared. Why? You have to check everything. On a list.
V plus E.
V plus E because you have to look at everything. Now the lower bound, a little trickier. Lower bound, best case on a matrix. Well, let's do a list first. On a list first, we want to know if there's a path. If you go to the very first vertex and there are no edges coming out of it, are you done?
Yes.
So what's the complexity?
Constant.
Constant. That one was easy. What about on a matrix? How long does,
You have to check every step.
Yeah, the V, because you'd have to go.
It's V because you have to check along to make sure that there's no edges coming out. So you have to go along the whole row. Yes?
How would this change if it was an edge instead of path?
If it was an edge instead of path, it would be constant.
Because you just need to check like one index, and if it's disproven, then you don't have to go with that.
Because now you're checking to see if there's an edge coming out of every, if there's an edge from this vertice to all other vertices. So as soon as, if the first one, there was no edge, you'd be done. There may not be an edge from this vertice to the other, but there could be a path to it that goes through another vertice. So you got to check all of them. Yes?
So there's two ways of finishing that. One is like to check that it's true and one that it's false. It's either case, right? So,
Yes.
Okay.
But when you're looking at worst and best case, you're looking at best case, what's the fastest way you could be done? The fastest way you could be done is you check the whole row, you find out there are no edges coming out of that vertex at all, you're done.
Okay.
That's the best case.
Yeah.
But the worst case is, let's say that there's an edge coming out on everything and not to the very last one. You got to keep checking because you're looking to see if you got the counter answer. So if you keep finding positive, you got to keep checking until you look through the whole V squared matrix.
And it's omega in the matrix because obviously you need to check every single one for sure. But
Yes.
Why is it not omega in the list?
What is it in the list?
It's O. Or did I misread it? Am I misread?
It's omega
no,
for each.
I misread this. I'm sorry.
So remember, the best cases are going to be omega, and the worst case are going to be big O. Because the worst case, you got a bound on it that it can't get worse than that. Omega is a lower bound that it can't get better than that. So be sure to put the big O in omega, or you will miss it. You'll get partial credit, possibly. Let G be a directed acyclic graph. What's a better word to say that?
Yeah.
And when you think of DAG, you think of
Topological source.
yes. Do I need to stand on the table?
Yes.
Might as well.
Why not? Yeah.
They just want entertainment, don't they?
Yep.
Let G be a directed acyclic graph on which a depth first search has been performed. I think Joe would think I'd be copying if I did this
Yeah.
one. Classify the following statements as true or false. Now, the vertex with the smallest pre-time. Now we're talking about a DAG or a non-DAG? We're doing a depth first search. We're talking about directed or undirected? You guys remember it. Good. Directed graph, acyclic. Okay, so the vertex with the smallest pre-time must be a source.
False.
Why?
Time doesn't tell us anything.
Pre-times don't tell you anything at all, just like she said. Pre-times tell you nothing. The vertex with the largest pre-time must be a source. Why not? Why not?
Times tell you nothing.
Okay, the vertex with the smallest post-time must be a sink. I thought we could just get the source from the largest post-time. Wasn't that the rule?
So you take the reverse.
So on a DAG, the smallest will give you a sink, the largest will give you a source. Is it the only source?
No.
Is it the only sink?
No.
If there is only one source, will it be the source? If there is only one sink, will it be the sink? If there was no source,
No such thing.
it doesn't exist. Right. Thank you. You guys are bright. On a DAG, there's always going to be at least one source.
Keeping them on their toes.
So,
They thought I was going crazy for a minute. Yeah.
so on a DAG you can learn about sinks through the post times, but on any other graph you would.
On a regular graph, if you run a DFS, you can run a DFS, and we've had discussions with the TAs and professor on this. If you you can run a DFS on a non-DAG. However, it is not. You can't do a topological sort from these pre-post times you get.
I don't think that's what
If-
he was asking.
If it's a DAG, you can get the pre-post times and do a topological sort. On a non-DAG, you can do a depth first search. The pre-post times will not give you a topological sort. What was your question again?
Well, it was whether you could determine sinks or not, but if you can't even topologically sort it, then that answers.
Right.
The problem is if your lowest post time were part of a cycle, then it wouldn't be a sink. So you can't necessarily determine that.
The vertex with the largest post time must be a sink. False. So it's false, false, true, false. Consider the following four functions. Log n squared. What's the first thing I'm going to do with that when I see it? Take the 2 off, put it on the front, and it's now log n. As soon as I look at it, that's what I'm going to do. Function 2 is n to the 2/3. Function 3 is n to the what? 1. N to the 1. Why am I saying n to the 1? Because I'm going to compare with n to the 2/3 and which one is higher. N to the 1 is higher than n to the 2/3. So I'm just going to mentally put that 1 on there so I can compare them. Then I have square root of n log n. How can we transpose that? N to the 1/2. Everyone remember your 8th grade algebra? I know, I forget too. So the square root is n to the 1/2. Which is lower, n to the 1/2 or n to the 2/3? So the highest one is what? What's our highest complexity? N. So we can put that last. What's our lowest? The lowest is log n. So now we just have the n to the 2/3 and n to the 1/2. But n to the 1/2 has this log on the end of it. So does that make n to the 1/2 a higher complexity since you're multiplying it by something? I might say I'm comparing 4 and 3, but if I multiply 3 by 7, then 3 is higher, right? So you're multiplying this thing that is a lower complexity, you're multiplying it by something. So does it make it a higher complexity now? Yes?
Don't you treat log n as constant root?
So
Do you?
like it has as doubling behavior. It's constant, right?
Increase by a little bit. So I'm looking for a word that starts with an I. 5 syllables.
Insignificant.
Insignificant. The larger n gets, the log is so tiny that 2/3 into the 2/3 is going to pass it up. Now when n is small, into the 1/2 is times something is going to be greater. But as soon as n gets large, it's going to surpass it. So we're going to say into the 1/2, log n, function 2 is going to be the second highest. Then into the 2/3 is going to be third highest. And then into the 1 is going to be fourth highest. Any questions on that? Consider this method G, which operates on an array of integers. The helper method choose randomly is also defined as well as the variable ran. A must be a non-integer. So we are doing a little problem here. We're saying cut equals 3. We have a base case here. We are looking, we have a for each loop. How many times does it loop? 9 times. Then we recursively call G again, right? How much do we break the array into? We break it into thirds. So B equals, A equals 9. And is there anything other than constants that are run in this first section, this first method? Everything is constant. But we are calling choose randomly, so we need to go down and check that too. Is there anything other than a constant run down here? Selection sort. What is the complexity of selection sort? If you have it on your cheat sheet, then you can look on your cheat sheet, or if you have it memorized, then you'll know. And she says it's n squared. Raise your hand if you agree. Raise your hand if you disagree. Raise your hand if you didn't raise your hand. Okay, those people who can't commit. So it is n squared, so D equals D equals n squared?
T equals 2.
T equals 2. So we have B equals 3. Log base 3 of 9 equals D equals 2. So what's the complexity? N squared log n. Because it's a tie. So you go into the D, log n. Then we move down, and he gives an alternative way. So now we're down here and we say, if you store 10 in cut, what is the new B going to be? 10? So B is now going to be 10. Log base 10 of 9 is what? Log base 10 of 9 is? Log base 9 of 9 is what? 1. Log base 10 of 9 is a little bit less than 1. That's all we need to know. We don't need to know the exact number. We just need to know that it's a little less than 1. What is D now? D is 1 because they said choose randomly. We're going to take that out. Remove the method choose randomly. That was the n squared algorithm. So we take that out. How, is it constant or is it n? N. Why is it n?
It's a dominating factor.
Huh?
It's a dominating factor.
But what makes it n? What in the algorithm is making it n?
Oh, yeah, the loop over.
This loop?
No, down there.
This loop?
Yeah.
Okay, that loop's making it in. Okay. So now D is 1. We have log base B of A is a little less than 1. D is 1, so our complexity is O of n to the 1, which is O of n. Great. Suppose that the first statement of the method G in the previous question, we just did that. You have two algorithms, A and B, for solving a problem involving an array. You know that A is faster than B for arrays longer than D. So you have arrays, let's use D as 100. When the array is longer than 100, then you know that A is faster. When the array becomes smaller than 100, B is faster. Right? So if you had a blended algorithm, you'd say, when the array got down to under 100, then you transfer over to B, right? That's what I'm thinking in my head, right? Even before I finish asking the question. So, B faster than B for arrays longer than D, and that B is faster than A for arrays smaller than D, where D is a positive integer. For each situation below, indicate whether A and B can be blended using the blending technique discussed in class to obtain a new algorithm that is faster than both A and B. So what needs to be done to A to where we can utilize B? If we're using A on an array of size 250, what are you going to have to do to A to where you're going to utilize B? Yes, you need to cut it. You need to cut the array in half. So that if you're chopping the array and making it smaller, what kind of method do you need? A divide and conquer. So if both A and B are divide and conquer, can it be profitably blended?
Yes.
Because A is being cut in half, and you could utilize B. Notice it said profitably. If it wasn't divide and conquer, you could still use the algorithm, but just never would use B, and it wouldn't be a profit to you. Neither A nor B is divide and conquer. No. A is divide and conquer, B is not. Will that help?
Yes.
Yes. Because A is the one that needs to be divide and conquer, right? And B is divide and conquer, A is not. Does that help? No. So it is yes, no, yes, no. 15. In this question, we will use binary notation. Suppose that the binary numbers, this one's fun. Now, I explained Karatsuba multiplication in the last review, and what? Nobody got it. Because I can't explain it in 10 minutes. So you may have to come see a TA tomorrow to explain it to you if the TA knows how to do it. But I'll try to briefly, should I even try? I'll try. Suppose that you have binary numbers 1011 and 1101 are multiplied using Karatsuba multiplication algorithm. What three pairs of numbers are recursively multiplied at the very top level of the recursion tree? Anyone have any idea how to do this one? You don't count. You do?
Yeah.
So, what are the first two numbers?
XL and YL.
So what's XL and YL in this number?
Which would be 10 and 11.
10 and 11. Does everyone understand that? You want me to write on the board?
Yes.
Yeah.
Go figure. Now, so we have, what are the numbers? 10, 11?
Yep. 1101.
And 1101. What is this? This is base 2. What does it equal base 10? Come on. What does this equal base 10? 10, 11. It equals 11. And what does this equal base 10? 15? 13. That's 13 base 10. So what it's telling, when you do multiplication, we'll try to get through this. Try to explain it the word can make sense. When you do multiplication, I'm going to try it in the base 10 first. If you multiply the first two numbers and multiply it by 100, multiply that number by 100, then you multiply the cross of these two and multiply it by 10, plus, then you multiply these two, and then you multiply that by 10, and then you multiply the last two together and multiply that by 1, and you add all that together, you'll get your answer. So we have times those two together, multiply those twos together. We have a cross multiply, then we have up and down multiply. So we multiply these two together, multiply it by 100. These two multiply by 10, these two multiply by 10, multiply these two, multiply by 1, add them all together, and we should get the multiplication of all of them together. So 11 times 13 is what?
143.
So if we multiply 1 times 1, you get 1. We're going to multiply that by 100. Multiply 1 by 1 is 1. Multiply that by 10. Then cross this way. 1 by 3 is 3. Multiply that by 10. Multiply 1 by 3 is 3. Multiply that by 1. This is really just 10 squared, 10 to the 1, 10 to the 1, and 10 to the 0. And you're going to get 100, 10, 30, 3, and it comes out to be 143. Now, Karatsuba multiplication cuts out one of the multiplications. These two cross multiplications, it cuts it out. And it says, just add these two numbers together, add these two numbers together, multiply them, then subtract this number and subtract that number, and I won't get into the details. It's in the PowerPoints. And then multiply that final number by 10 to the 1. You get the same answer. So let's try it. 1 plus 1 is 2. 1 plus 3 is 4. Multiply those together is 8. 8 subtract 1 and subtract 3. So this would be called in the PowerPoint P1, and this is P2. And this comes out to be P3. This is P3. So you have to take P3 minus P1 minus P2, which is 8 minus 1 minus 3 equals 4. And then you take 4 multiplied by 10 to the 1, and you get 40. And then you add P1 plus P2 plus P3, and you end up getting 143. P1 is 100, P2 is 3, and P3, after you calculate it, you get 40. So you add the two top ones together, you add the two bottom ones together, you multiply them together, then you subtract P1, and that is P3. Then you subtract P1 and P2, P1, P2, you get this new number, multiply it by multiply it by 10 to the 1, and you get 40. So now, how do we apply it to this? We can divide this in half this way. So this is the left and right. So the first multiplication is top and bottom. So the first multiplication is 10 and 11. So that's the answer to one of the questions. Just like we multiplied 1 and 1, we're multiplying 10 by 11. The second one is multiplying the second half. So you're multiplying 11 by 01. 11 by and 01. And actually answer, you just put one of the two numbers you multiply. 10 and 11, base 2, and 11 and 01, base 2. And what is the third multiplication? Using that rule for P3, what would be the third set of pair of numbers that you multiply? Excuse me?
XL and XR, is this?
Remember I added those two together, and then I multiplied them. So how would you do that here? So you would add 01 and 11 together. And what do you get? You get what? 101. And then you add 11 and 01 together. And what do you get? What is it? 1110? Is that correct?
No, it's 100.
I'm just trying to remember. It is 0, 0, 1. 1, 0, 0, I mean. Okay. So those are the two numbers. So this is actually the answer to the question. What are the three pairs of numbers you multiply? Now, following through and adding it up, if you finished with how I added things up, you would also get 143 from this binary. But I'm not going to do that because it would take too long. I'm moving out for a picture. So those are the three sets of numbers. If you want more detail on the Karatsuba, there's the PowerPoint, or you can come talk to a TA tomorrow if they know how to do it. Yeah.
I guess maybe it's too broad, but how specific do you need to know that algorithm? Like what are the past that?
Joe just asked for the three pairs of numbers. I explained the whole algorithm, but he didn't ask to know the whole algorithm. But who knows what he's going to do on the test? You never know. He may have you do the whole thing I just did. I don't know. I doubt it, but he did ask for the three pairs of numbers. One pair of binary numbers, another pair of binary numbers, and one more pair of binary numbers. Okay, in this question and the next, you will be designing an algorithm for directed acyclic graph. What's another name for that? What's the first thing you think of? Such as the one below. Let singleton U be true if vertex U or one of its, this should say descendants. It's a typo. In the answers it says descendants. In the solution.
Descendants meaning like children?
Yes. True if vertex U or one of its descendants has exactly one vertex leaving it, and false otherwise. So before I even finish reading on, does A have one vertex leaving it? Does vertex A have one edge leaving it?
No.
Does one of its children have one edge leaving it? Yes, B does. So to calculate A, don't you need to know B first? So how would a topological sort help here? You do the topological sorts and calculate them all backwards.
I want to clarify, doesn't descendants mean anything, not just direct children, but anything beyond that also?
Yes.
Just to clarify.
Descendants would be children, grandchildren, great-grandchildren. So if B didn't have one thing coming out of it, but D did, A would still be true. So let's look at D. Does D have one edge coming out of it? Does any of its descendants? It doesn't have descendants, so it's false. Same as E and G. But B has one edge coming out of it, so it's true. You don't even have to look at the descendants. C has more than one coming out, and both of its descendants have nothing, so it's false. A is true because although it has two edges coming out of it, one of its descendants, B, only has one edge coming out. Yes.
So when we write these, are we going to be allowed to use like topological sort as like a function when we're writing it, or do we have to like write out how it works?
No, he's gonna. Let's wait. The question will come, and you'll see how it's working. Let singleton U be the true of the vertex U, or one of its descendants has exactly one vertex leaving it and false otherwise. The graph above is annotated with the solution for each of its vertexes, the true and false. For example, singleton A is true, singleton C is false. Let edges U be an array consisting of vertices reachable from U via exactly one edge. So edges A is a list that includes B and C. So it's just the children, not all the descendants, just the children. The edges that you can reach with exactly one edge. In the graph above, example, edges A equals a list including B and C. Does that make sense? This is one of those questions that takes 20 minutes to read and 2 minutes to write the answer. And edges E equals an empty set. E, there's an empty set there. We need an algorithm to efficiently compute the value of singleton U for each vertex. So are you going to write a program that will do every single one of them all together? No. You're going to do it as a single vertex. We need an algorithm to efficiently compute the value of a singleton for each vertex of any DAG. Okay. Below, compute the pseudocode for a method that takes the vertex of a graph as its parameter and stores a value in singleton U. That one's a little more clear. You take one vertex and then you report whether it's true or false. So if you wanted to do singleton A, wouldn't you have to do B and C first? I mean, if you did B, you'd have to do D before B, right? And if you did B, C, you need to do D and E first. Does F and G need to come before this group on the left or after?
It wouldn't matter.
It doesn't matter. Exactly. It doesn't matter. F needs to be before G. You could have F and then everything in the middle and then G at the end, or F and G at the beginning of the topological sort, or F and G at the end. It doesn't matter. As long as F is before G. And to finish off the question, your method must be implemented so that when it is applied to each vertex of the graph, in an order you will specify in the next question, the entire singleton array will be filled correctly. Assume that the singleton and edges array already exist. That's just so you don't say you don't create them in a line of code. Just assume that they already exist. And are accessible to your method. Your method must be O of n. Not n squared, not log, but n, just n. Where n is the length of edges U. So here's the space, and then you write your code. So I'm going to show the code up here, and I even got upset when I saw Joe's code because it was so elegant. And mine had like 3 or 4, 5 lines of code, and he did his in like 3 lines of code.
So, real quick, so it says that this question's worth 6 points. Is that 6 points for this page or 6 points for this particular question?
Let's see. 6 points for this question. Okay, so there is. There is the code. So you're going to run it on one. This works for one vertex only. So you say singleton equals edges U length equals 1. That tells you if there's one edge coming out of that particular vertex, right? If there's more than one edge, what are you going to get back? It's going to equal false, right? And they should already be defaulted to false anyway. So if there's one edge coming out of it, it's set to true, and then you're already done. You really don't even need to do the rest, but he just has the rest of the code run anyway. For Now he's going to look through all the edges that are coming out of that particular vertex. And he's going to say, am I true, or is that child that I'm looking at true? And if either of them are true, then I'm going to be true. Why does he even include this? Why does he include that with the or? Why not just say it equals singleton B?
Because if you had children A, B, C, and A was true but B and C were false, when you iterated through, B and C would then change your answer.
It would set them back to false. So we need to say, keep looking at myself, and as soon as I get set to true, I'll stay true. Because I'm looking at myself and the children. Does that make sense? And that's it, 3 lines of code. And I'll bet you on the test, there's not one person that had 3 lines of code. Everyone has 10 lines of code and loops and all kind of for each loops and everything. So, really elegant code here. I'm highly impressed. Let's go back to 17. How are we doing on time? Do you guys need to take a break? Raise your hand if you need a break. You can't take a break, Aaron. You're just sitting there. You don't even have to think, man. Okay, now, and I've already asked this question like 10 times, so here's the question in paper. In the box below, specify the order in which the method from the previous question must apply to the vertices of the DAG. Everyone say it together? Reverse topological sort. Got it. So the directed graph X diagram below is the subject of the next 4 questions. So there is, did he say DAG? Is it directed? Is it acyclic? So it's not a DAG. The directed graph. So are we going to do a topological sort on it? No. But can we do the depth first search and post and pre-times? Suppose that you do a depth first search on breadth first search, sorry, on X beginning with vertex H. How many vertices are incorporated into the resulting BFS tree? So if we start at H, there's a total of 10 vertices. How many are we going to look at? Yell it out.
8.
Anyone say anything other than 8? Sometimes people say 6. Well, let me see. We start here. Can we ever get to C or A? No. So we're just going to look at everything else. It's 8. How many edges are in the longest path of the resulting BFS tree? So let's start at H. It says how many edges. A lot of times people look at, well, how many levels, how many vertices. We want how many edges are in the longest path. So we have H. The next one we go to is I, so that's 1 edge. Then the next level would be E and D, so that would be a second edge. So then E would go to B and F, that would be a 3rd edge. And then F would go to where? G and J, that would be a 4th edge. So how many? 4. So we got 8 and 4. Suppose that you do a depth first search on X. Suppose also that whenever there is an arbitrary choice of vertices to visit, either with DFS or Explorer, you always pick the one that comes first in the alphabet. Give the pre and post numbers requested below. The lowest pre number is 1. Sometimes people put 0 first. Always put 1 first, or you will miss every single question. Raise your hand if you do not know the difference between DFS and Explorer. Do I need to write it on the board? Raise your hand if you want me to go over it on the board. Okay. Okay, so DFS is going to run, and then you're going to do a for each loop of all the vertices. in alphabetical order. Inside that for each loop, you're going to visit. You're going to check to see, check that the vertices are visited or not, check them out. And then you're going to call explore. So DFS calls explore. Down here you have explore. And in explore, you are going to do another for each loop of all the V's. You're going to visit and check it whether it's been visited. If it's been visited, you skip it. If it hasn't been visited, you mark it as visited now. And down here, you do an update. So if I have a graph that's A, B, C, D, E. When I call DFS, which vertex am I going to reach first? And then which additional vertices am I going to? I'm going to call explore on A. And then explore is going to look at what vertices? It's going to look at B and C in addition. Then what? And it's going to update these. Then what happens after I'm done with C? Then when I'm done updating, I'm going to go back up the DFS, and I go into the second loop of this for each loop. And then which is the next vertice that hasn't been visited in alphabetical order? D. Then I go to D. Explore will examine how many vertices? How many? 2. D and E. So DFS loops twice. Explore is called twice. So if he asks on a question, how many times is DFS loop called on this, the for loop, you'd say 2. Now if it was directed, how many times does DFS call explore on that graph? 5 times. And each time it calls, it's only going to explore one vertex because it can't go backwards. Now, if you went in reverse alphabetical order, how many times would it be called? Once. Okay. So you guys got it now? Crystal clear. So I'm not going to do the pre and post times because I feel everyone knows how to do that.
Starts at A.
Starts at A, alphabetical order, with the number 1 pre-time.
Well, question 18 says start at age, so it kind of assumes that you keep starting at age. So like when I first did it, I got all of them wrong because I started at age instead of starting at A, but it also says you should come first in the alphabet.
Yeah, on this question it said start with age. Down here it said suppose that whenever you have an arbitrary choice, do it in alphabetical order. So different questions start at different vertexes. So you just do it, give the pre and post times and label them on here, and that's it with those questions. How many strongly connected components does X have? Yell it out if you know it. How many strongly connected components does that graph have? 8. Well, okay, I'm going to count them. Let's say E, B, and D is 1. F, G, and J is another one.
No.
It's not?
Directed, the direction.
Okay. So that means this is the only group. E, D, and B are the only group that is greater than 1. Everything else is a single strongly connected component. A strongly connected component group can exist of only one vertex. So there's 1, 2, 3, 4, 5, 6, 7 singles, and then this group of 3 is the 8th one. 20. The next 3 questions concern this directed weighted graph Y. Suppose Dijkstra's algorithm is used on Y. Find the shortest path tree rooted at vertex E. Yes?
So when it says shortest path tree,
that means that as you're going through, you should be giving each node a level that it's on from the tree, correct?
Yeah.
So that way you don't.
Well, if you got a tree and you're building a tree, the branches don't go back together. So it's going to be a dag, basically. And it's going to go out. No, it's not going to be a, it might be a dag, but a tree. Nothing is going to go back and touch each other. A tree is a dag, but a dag isn't necessarily a tree. Right, Aaron?
Sure.
Okay, so suppose that you do the algorithm. Suppose Dijkstra's algorithm is used on Y to find the shortest path tree rooted at vertex E. The first vertex to be removed from the primary queue, prior to Q, is via a deletement operation is E. So first you put E in, you remove E, that is the first one. When you remove E and you update E, to update all the children of E, what are the three vertices that go in the prior to Q?
4, right? Should be 4 vertices here.
B, D, F, and H. Which one has the lowest number? B is going to have the lowest number. So the second thing you pull out is B, right? But when you pull out B, you got to update which two vertices? A and C. A will go in as 9. C will go in as 5. So what's now the lowest? H is going to be the lowest. Because it's going to be 4. C will be 5 second. So the third one you pull out will be H. So the answer to the first question is H. And then you just keep doing updates, pulling out the first thing, the lowest thing in the queue, and doing updates. And there will be some updates when you pull things out. So be sure to. I'm not going to go over all the steps because we're probably going to. Does anyone want me to do Dijkstra's on the board? Thank you. Everyone has it down perfectly? So you, and then, so you're going to, out of the 9 vertices, you're just going to list all the odd ones. 3rd, 5th, 7th, and 9th. And then the last question is, suppose that a distance array for graph Y has distance E equals 0, and that all the other entries are infinite. Suppose that the update operation is called on these edges in that order. Below give the resulting value of the 4 elements of the distance by completing the table below. So, if we do an update on BA, is the array going to change? In what way? If it does. E equals 0, everything else equals infinite. Now we're going to update BA. Does anything change? No. Array stays the same. Right? Right?
No.
No? What changed?
Updated to 6, the edge between B and A.
Okay, A is infinite, B is infinite. So does infinite plus 6, is infinite plus 6 less than infinite? Okay, so there's nothing changed. Because if you're updating BA, you're going to say B plus the edge 6. So infinite plus 6. If that is less than infinite, then you'd update A. And it is not. So after the first update, nothing changes. Now we're going to update E to B. What changes? B changes to 3. Now we're going to update BA again. What changes? A changes to 9. Now we're going to update DG. What changes? Nothing. Now we're going to update ED. What changes? D becomes 16. So we have B at 3, A at 9, D at 16. And then and then E. So A, B, D, and E have been updated, and it asks you what those values are. A, B, D, and E. So that's the last one. You have a question?
Since we're like just about done with the review, I know this is longer than what it's going to be on Thursday, but how do people do generally? This seems like a ton of stuff.
Oh, this is a brutal test. I will give you that. This test is brutal. And it's long. But Joe said the test on Thursday will be shorter. But consequently, if it's shorter, then the questions are probably going to be harder.
You had Joe before? These tests are usually hard.
Yes?
So other than the master theorem and all the algorithms, what else should we put on our cheat sheets? Inspirational quotes.
Matt, okay. I didn't hear that. What's that?
Inspirational quotes.
You can do it.
Go look up a Gandhi book. So, yeah, the master theorem, the best, worst, and average of all the algorithms you can think of. I'd put topological sort. Some of the graphs you've done, I'd put a simple, like a topological sort. I'd put explanations on insertion sort, selection sort, maybe explain how they work. And maybe just do an explanation to remind you how they work. What else would you suggest? What's your question?
So since we had like some on this, there was somewhat of an implementation question on the Karatsuba one. Should we expect something for like Bellman Ford as well? Like something based on how it
Should we
works?
know how to implement every single one of the...
I would know,
Okay.
because you don't know which one he's going to put on.
Yeah.
He may have nothing on Karatsuba and say, I've seen tests, 4150 tests where you had to implement a Bellman Ford. And he asked Bellman Ford questions. He hardly asks any Bellman Ford questions on here.
Yeah.
You know, he'll say, what's the most amount of times that you have to run a pass on Bellman Ford? What's the most? V minus 1. What's the least? Huh? These are possible questions. What's the least amount of times that Bellman Ford has to run a pass? That's for a regular Bellman Ford. Was that your question?
No, my question was, isn't the Bellman Ford really similar to Dijkstra's, except for you don't pull the minimum off the priority queue, you just pull off whatever's in the front?
Bellman Ford works with negative edges. So that's why the complexity is so bad.
Right.
Because it will allow you to work with negative edges. There are 3 shortest path algorithms. Can anyone name them? Depth first search? Breadth first search? Is that one?
Kind of.
It's only a shortest path if the edges aren't weighted. So what are the 3 shortest path algorithms for weighted graphs? Dijkstra, Bellman Ford. What's the third one? No, there's 3.
A star? That's the only thing I can think of that we haven't talked about.
Huh?
It's unnamed.
It's unnamed. It's just called the shortest path on DAGs. It's got great complexity, but it only works on DAGs. Dijkstra works if it's not a DAG, Dijkstra will work, but the limitations for Dijkstra is it can't have negative edges. If you have negative edges, then you have to go to something with even worse complexity, which is Bellman Ford. If you have negative cycles, you can't use any of them. Because it's impossible to find the shortest path with negative cycles because you just keep circling. So the 3 shortest paths, that could be a question. Depth first search, explore, breadth first search. Be familiar with all these algorithms, the complexity, the pre-post times.
Greatest common denominator questions be on there.
Greatest common divisor.
Divisor, that's one.
Yes, I would guess that it's going to be on there because it wasn't on this test. So Joe's probably going to say, oh, it wasn't on this test, now let me put on the next one. Yes?
Just correct, I'm pretty sure Bellman Ford does work on negative. That was one of the pros over Dijkstra's. Dijkstra's can't be negative.
Yes, it does work on negative edges. It doesn't work on negative cycles. It works on negative edges. Dijkstra doesn't work on negative edges. Bellman Ford does. but none of them work on negative cycles. Hold on.
If we have time, we could do a quick example of doing like the mod for a negative exponent.
Yes, I can.
I was just going to say, I'm pretty sure Joe said this test only covers up to modular arithmetic, so GCD
Yes.
shouldn't be on there.
So what?
I don't think GCD is on there.
He's suggesting that GCD won't be on the test because it came after the modular arithmetic, and there's only going to be simple modular arithmetic. So, if he's correct, GCD won't even be on there. It'll just be on the final.
I'm pretty sure that's what he said in class. We can
Yeah, he did.
clarify that. Okay.
So GCD was it on week 6? He said up through PS6, I think, will be on the test.
Yeah, PS6 wasn't on
Okay.
GCD.
Yes.
Should we expect any questions based on like caddis implementations?
I doubt it. He could. Who knows what's going to be on the test? People always ask me what's going to be on the test. I say, not only I don't know, but Joe doesn't know because he hasn't written it yet. He'll probably write it tomorrow.
I'm sure he's in a really good mood.
Yeah.
Yeah, I should go buy him dinner or something, get him in a good mood.
I mean,
I don't know, that might be
I'll
worse.
voice
You want me to do an example of the mods?
This was the negative, not the negative mod, but like to a negative.
The inverse?
Yeah, the inverse. That's totally.
The inverse, okay. I'll do inverse.
Because like, the way that he described it is to try to find a multiple where the multiple is one more than what you're modding it by, but like,
Right.
usually that doesn't make sense.
So let's do 7 mod 5. The first thing you got to check to see if there is we want the multiplicative inverse. First thing we want to do is see if the GCD, and since this has GCD in it, it probably won't be on the midterm according to Aaron.
Oh,
Well,
this
wait.
will be. This will definitely be on the midterm.
Okay,
This is
because yeah, you don't really have to do the GCD.
Yeah.
So, you want to do multiples of 7, and in your head, do multiples of 5. See, 7 mod 5.
Will it be 7? Because 7 is like, it's 2 mod 5?
Well, not when it's inverse.
You want something that you can multiply 7 by, so when you mod it by 5, you get 1. So what's the inverse of 5? 1/5. Inverse of 7 is 1/7. When you multiply by it, you get the number 1. And multiplicative and modular inverse, it's a number that you multiply this by, and then mod it by this number and get 1.
I'm saying, can we simplify 7 to 2?
Simplify 7 to 2? No.
Okay.
Not on the inverses. So if you do 7 mod 5, you're going to get 2. So we're going to look for multiples of 7, and we want multiples of 5 that are 1 less. Right? So if you had 6 mod 5, you'd get 1. So you want the multiples of 5 to be 1 less than the multiples of 7. So is this going to be an easy one there?
Yeah,
Yeah.
it's 3.
So you could do multiples 14, and you want it to be 1 greater than a multiple of 5. 21, 28, 35, 42,
You might want to back up.
and here. So at 21 mod 5 is 1. So you just do multiples in your head until you run into 1. 21 mod 5 is 1. You had to multiply 7 by 4.
3.
Oh. I failed 3rd grade times tables. You multiply 7 by 3 to get 21, and so the multiplicative inverse is 3. Because so it's what you multiply 7 by to where when you mod it by 5 you get a 1. So if I just randomly think of 2 more numbers, 3
Choose carefully.
Choose carefully.
We could be here for a while.
11, I know. 11 mod 7. It's usually forever.
Get an inverse?
Is that too big?
Right.
Inverse, inverse, yes. Inverse.
2.
It's too small.
So you multiply 11 by 2, you get 22. 22 mod 7 is 1. So the inverse is 2. So you find multiples of this number, multiples of the mod number, and you need to find a multiple that is 1 more than the multiple of a mod number. You just do it in your head. The numbers on the test will be small enough to where you can do it in your head. There is an algorithm in the PowerPoint that you can run, but don't use that when you're trying to use these numbers because they're too small to do the algorithm. The algorithm would be much harder. So just do it in your head. Yes?
Why is it 1? Like, why is it that you're trying to get 1 out of it?
Because that's just what the multiplicative inverse is.
Okay.
All this will come to fruition when we do RSA. All these things we're learning, you're like, man, why are we learning this? When we do RSA, it's all going to come. And you're going to have to do a big RSA program on the calculation on the final. And it's going to be using GDF and multiplicative inverse and all these things. Yes?
Will you ever give us one, like, for example, 7 to the -2? Like, what's the difference of those again?
7 to the -2?
Yeah, like...
I don't think we ever did before.
I don't even know how to do that.
It's always the -1.
The inverse is just -1. There's never one in -2. There is a...
For example, like a 4.
If you do... let me explain another thing to you. I'll re-explain it to get it cemented in your head. 11 mod 7, what's the answer? It's 4. Now, if you add 7 to this, what do you get? 18. If you do 18 mod 7, what do you get? If you add 7 again, 25 mod 7, 4. All of these numbers are congruent. So with all of these modular tricks, you want to look for congruencies, especially when you get those numbers with the long exponents. Also, you can subtract 7. So you get 4 mod 7 equals 4. What's the next one up? Minus 3? -3 mod 7 equals 4. Now remember, your computers do modular arithmetic incorrectly. What they do, if you're trying to do the -3 mod 7, it negates this, does the mod, get an answer, and then it negates it back. So you end up with 3. But -3 mod 7 is not 3, it's 4. So if you don't know how to calculate, if he has on the test -3 mod 7, what's the way you can figure it out? Find a congruent number. And the way you find a congruent number is add or subtract the mod. So you add 7, add 7, add 7. Now all of these numbers are congruent. They all come up with the same answer. So find a congruent number that's easy. So if you have a negative number, if he says, give me -300 mod 7, you just keep adding something to 300 until you get a positive number, and then you calculate it then. Now, he won't even have anything that big of a number because everything you'll be able to do in your head. You won't have to use a calculator. Yes?
Just to clarify on Piazza, somebody asked already, and it will not cover GCD or modular inverses.
Aaron is correct. Yep. But there will be modular arithmetic.
Well, yeah.
Not modular inverses.
No inverses? So no inverses, but the other mods.
It was still fun.
Well, now we're ready for the plan.
Any other last questions before we leave? Where it's going to be? Do you want to text me any questions? No, she has an illness. She can't talk. Her throat is sore. Okay, you're good. Anyone else have any final questions? Who's kind of nervous for the test?
Joe's test.
Joe's test. Good luck. If you have any questions, I'll stick around for 5 or 10 minutes. So we're done.